Good afternoon, everyone. Thank you for attending this talk. My name is Masood Rahman. I'm a faculty member from Dalhousie University in Canada. So today we are going to present our work where we incorporate cognitive debugging abilities into the AI agents to localize software bugs. Now, this work was done by my PhD student Asif Samir, and I'll be presenting the work today. Now, clearly, we do not need a separate introduction about software bugs, but let me present you one bug report from Apache-based system. So here the bug is that after a successful rollback operation, the fail-safe version of a table should be removed, but for some reason it is still there. Okay. Now, if we look at the code, so this method should be invoked, but for some reason it is not invoked. So let's take a look at the code. So here you can see this is the first attempt for the restore operation. And if the restore operation fails, then the code is trying to do the rollback operation. And interestingly, after a successful rollback operation, rather than deleting that fail-safe version of the table, it is throwing just another new exception. And that is why there is no direct path to this particular method that is responsible for deleting that fail-safe version. So you can see this is a bit complex bug, and the traditional approaches are not doing very well. So we try to localize this bug using the existing baselines, and you can see they are not doing very well. So as you can see, we need some level of understanding of the code, and we also need some level of, let's say, developer level cognitive abilities into the agents to understand and localize this bug. Okay. Now, besides this, we also found several other challenges in the existing techniques that we investigated. So these are three most recent techniques are tackling with a similar kind of problem. And what we have found that many of these techniques are trying to determine the fault proneness of a program element in isolation. So that means they are not considering the dependency of that program element. But we know that fault can propagate from one element to another element, but they are not considering that level of dependencies. Then we also found that many of the agentic solutions are trying to explore the code base for different kind of tasks, for let's say bug localization, but they are not reasoning about the root cause of the bug when they are doing that code level exploration. So that is another issue. And then we also have found that the effective context management for any kind of LLM-based solution is also a major challenge. So we try to address these three challenges in our technique, and we came up with this technique called CogniGent. And here you will see that we have incorporated multiple agents, and different agents have their different capabilities. So first, we represent the code as a graph, and for this we use Neo4j library. And in this graph, we have multiple nodes, and each node is basically a method, and the edges are basically their syntactic dependencies. So let's say caller-callee relationships, or let's say inheritance relationships. And then we introduce our agent called restructuring agent. So you see in the bug report, you will have different information in an unstructured way. So this guy will be responsible to make the bug report structured. So that means what is the faulty behavior, what is the expected behavior, and what are the steps to reproduce. So it will structure those information. And using this structured bug report, then our retrieval agent will retrieve a set of candidate code segments based on textual as well as semantic similarity. Okay, and this is a very well-established practice by the existing literature. But as you can see, the retrieval agent will rely on simple textual and semantic similarity, which might not be enough. So that is why we introduce another agent called filtering agent. And this guy will look at those retrieved candidate code segments, and then it will try to determine the relevance with that restructured bug report with the help of an LLM. Okay. And after this filtration operation, we'll get a filtered set of, let's say, candidate code segments. Then we introduce another agent called hypothesis agent. And this guy will be responsible for hypothesis generation. So that means it will look at the candidate code segment, and it will also look at the faulty behavior in the bug report. And then it will try to hypothesize about the root cause of the bug. So it will try to generate a hypothesis that will connect that bug with that candidate code segment. Okay. And then we introduce another agent called investigator agent. And this agent will be responsible for, let's say, capturing the evidence. So like the real life investigator, this agent will capture relevant evidence to either, let's say, accept or reject that hypothesis. So what it will do, it will look at that candidate code segments, and then it will ask itself, do we have enough information to prove or disprove this hypothesis? So if it finds that we do not have enough information, then trigger another agent called exploration agent. And this agent will be exploring the code base to gather evidence. Okay. So that means in that candidate agent, you will have this different method invocation. So it will go through each of those method invocation, and it will try to generate a call chain as an evidence. And it will basically use a depth first search, and it will try to generate a call chain, and at the same time it will also measure the confidence of that call chain against that hypothesis. Okay, so that means at the end of this exploration, for each of the candidate code segment, we'll get a call chain with some confidence that is telling that how likely this call chain is going to prove or disprove that hypothesis. Okay, so now after that, we also introduce another agent called observer agent, and this guy will look at the code segment hypothesis as well as the call chain with high confidence, and then it will also produce another confidence score. Okay, so we are basically using LLM as a jazz in this context. Okay, so now we have for each of the candidate code segment, we have at least two confidence scored against their hypothesis that we have generated, and then we combine those confidence score to generate the final ranking for the code segments. Okay, and this is how we generate a ranked list of faulty code segments against that bug report. Now, clearly, I will not have enough time to explain the result in details. For that, you have to read the paper. But we try to answer these 4 different research questions, and we used 591 bug reports, and we have used multiple LLM code for our experiment, and we have replicated 5 different baselines, and we have used the usual metrics. And as you can see that the performance that we got is the highest when we use the depstral as the LLM code, and obviously we got higher performance when we consider document as the fault unit. And we also have found that our technique performs well, especially when we have some kind of hints within the bug report. And we also measure the impact of our technique against the number of faulty elements. So let's say how many documents are affected by this fault. And we have found some interesting pattern there. Then we also measure the impact of different agents that we have incorporated, and you can see that they are contributing significantly towards the overall performance. And then we also compared our technique against different baselines, and as you can see that our technique was able to outperform the baselines. So let's do a bit of summary. So what we have seen is that to localize the bug, simply looking at the code is not enough. So you have to look at the whole context within the code base to understand the bug and to localize the bug. Then we have also seen that the localization is not a single shot activity. So it's a kind of iterative process. So you have to generate the hypothesis, you have to collect the evidence, then you have to test the hypothesis before reaching any conclusion. And we try to incorporate that behavior within the AI agents. And we also see that the performance can vary based on different granularity, but we have to choose that granularity carefully. Anyway, so that's a bit of overview of our work. Obviously, to learn more, you have to read our paper, and I would be happy to answer any questions during the actual QA session. Thank you, guys.